whereby atoms of an element exhibit the same atomic number but different mass number. What am I saying? So if you are having, let's say, atom X, atoms, let's say you have an element X with, or an element W with atom X and X. So we are talking about isotopes. It means that they will definitely have the same, let's say the atomic number of this is A. The atomic number of this one will definitely be A. But what will change, if the atomic number of this one is Y, automatically the atomic, if the mass number of this one is Y, the mass number of this one can now be Y plus 1. So what we are saying is that when two atoms of an element exhibiting isotopy, the mass number will definitely be what? Will be different, or the mass number differs while the atomic number remain the same. And let me quickly give you examples of elements that exhibit isotopy. Chlorine is one of them. Chlorine is one of them. Oxygen is one of them. Sodium is one of them, e.t.c. So this one is a special case. We normally call, when you ask us what is the relative atomic mass of chlorine, we will say it's 35.5. It is derived from this concept of isotopy. That is why the relative atomic mass of elements are not relative atomic mass of, or relative atomic masses of elements are not whole numbers, simply because they exhibit isotopy. That is why you can never have them as a whole number. If you are given the relative atomic mass of a particular element, it will always be to decimal, because they can never be whole numbers, simply because they exhibit isotopy. So when you have 25% of chlorine 1737 and 75% chlorine 1735. In this situation, if you want to calculate the relative atomic mass of these isotopes of this chlorine, it's just like saying relative atomic mass will definitely be 25 over 100 times 37 in a bracket, then you have a complex bracket this way, plus 75 over 100 times 35, then you put a complex bracket. Then at the end, you discover that this one, when you sum this with this, you will approximately get 35.5. That is why the relative atomic mass of chlorine is 35.5. Now, perform simple calculation on relative atomic mass, and that is a typical example of what I have done. Even in our previous exercises, we have also treated a question related to this type. So in this situation, we have been able to use this format to calculate the relative atomic mass of chlorine. So it should be noted that each time you are asked, sometimes they can possibly omit this. They can possibly omit, they can give you the relative atomic mass of a particular isotope of an element, and they will now give you they can give you 25% of, let's say, X17. You now put probably Y here, and the other one too, and let's say X17 35, and the question asks to determine this, that's Y. So in this situation, we can also follow the same trend, but this time around we are going to make what? Y the subject of the formula. So we have 25 over 100 times Y plus, this is, let's say, 75%. So you have 75 over 100 times 35. So in this situation, we're not going to make this y the subject of the formula. We have done a couple of these examples in the previous exercise, and we are still going to look at them in the subsequent exercises. Now, the next one is determine the number of electrons in s and p orbital. We know that we have s orbitals, we have p orbitals. So the question asks us to determine the number of electrons in s orbitals as just one. So in this situation, the maximum number of electrons that you can have for x orbital will definitely be 2. Take notes. The number of electrons you can have for s orbital will definitely be 2. So in this situation, you have maximum of 2. In the case of the p orbital are degenerate. P orbitals are degenerate. What do I mean by they are degenerate? That means they have 3 suborbitals of equal energy. What am I saying? In the p orbitals, you have a scenario like this where you have 3 suborbitals. The first one is px, the second one is py, and the last one is pz. In this situation, each suborbitals must be occupied by 2 electrons. 2 electrons. 2 electrons. By, you know why I'm inversing this? Because of what? Pauli exclusion principle that states that no 2 electrons in an atom must have the same value for the set of quantum numbers. That means no 2 electrons are identically alike or the same. So if one is spinning up, the other one has to spin down. So in this situation, we have 2, 2, 2. That's making it 6. So that means the maximum number of electrons we can have for p orbital is 6. Now, the question still move further to also enlighten us. And here we have relate atomic number to the position of an element in the periodic table. Now, elements are placed in group based on the valence electron or outermost electron. Elements are placed in period based on the number of shells. So let's pick some set of elements. Let me pick nitrogen, sodium, and calcium. In this situation, what is the atomic number of nitrogen? 7. What is the atomic number of sodium? 11. What is the atomic number of calcium? 20. So by Bohr model, we know that because Bohr by near Bohr model, we know it is a shell arrangement of an element. So in this situation, by Bohr model, we're going to have what? 2, 5. By Bohr model, we're going to have 2, 8, 1. By Bohr model, we're going to have 2, 8, 8, 2. In this situation, this particular element will definitely belong to what? Group 5. Why? Because the valence electron is 5. Or the valence electrons are 5. Now, what period? The period will be based on the number of shells. You have 1, 2. So this one will be what? Group 5, period 2. Let's move to this. We have only one valence electron. So this one will definitely be what? A group 1 element. How many? What is the number of period? 1, 2, 3. We have 3. So it will be in period 3. Also this, what is the valence electron here? 2. This one will be a group 2 element. What about period? 1, 2, 3, 4. So this one will be a period 4 element. Then let's now talk about identify reasons for variation in properties across the period. There will definitely be, because we have how many properties? We have, the first one that we have is atomic radius. Atomic radius. We have ionization energy. Ionization energy. We have electron affinity. We have electron affinity. We have electronegativity. Electronegativity. So if you look at this trend, you discover that this one increases down the group but decreases across the period, while this one decreases down the group but increases across the period. This one decreases down the group, increases across the period. This one decreases down the group, increases across. That means out of these four properties, only these ones, they are together. Only this one is odd. That is, it's only this along here that you have what? Increase down the group, but it decreases across the period. And the major factor that affects or determine the change across the period is what is known as nuclear charge. What is nuclear charge? Nuclear charge is the relationship between the positively charged nucleus and the electron revolving around the nucleus. Because inside the nucleus is positively charged, because the charge of the nucleus is assumed by the what? The proton. While the outside, what is revolving around, is negatively charged. So the attraction between the positively charged nucleus and the negatively charged electron revolving around is what we call the nuclear charge. So as the distance between this and this become smaller, the attraction is more. And as the distance between the positively charged nucleus and the negatively charged electron is wider, then the attraction becomes less. Take note of that. So what accounts for the decrease or increase in the case of these ones, decrease in case of this one, increase in case of across the period, is the effect of the nuclear charge. It is not enough to get these topics treated. It is a different ballgame when we see questions and we are able to apply what we have learned